Hello, welcome to Math with Beth, and I'm going to show you in this video some of the ways to use E and also ln, the natural log, especially when starting to use some of this in calculus. So if you don't know anything about E or ln, you might want to watch a different video to give you more of an understanding. This is supposed to just be a quick review. So first, the letter E is really a number. It's similar to how we use pi because it's a number that goes on forever. So we just gave it a name. So E is about 2.7, but technically it goes on and on. It is typically used with exponential growth or decay, typically when finding interest rates or just how something grows at an exponential amount. So here's one quick example. This is for continuous growth. This is used again in interest rate equations. So in this case, the P is your initial value. The E we just talked about is an actual number. R is going to be your rate, but you're going to need to make it a decimal. And T is your time. So in this example, Lewis invests $5,000 in an account. So this is going to be the P that earns interest at an annual rate of 3.27%. So we're just going to have to change that to a decimal. Find the future value. That's the answer that you're basically getting of Lewis's account, or Luis, sorry, after 5 years if the interest is compounded continuously. So that's just your hint to use this equation. So to get the future value, so I don't really need to put anything over here, I'm going to do 5,000 times E raised to the 0.0325, because that's the percent changed to a decimal, for 5 years. So I'm going to need to multiply that by 5. So when you do this, you just need to be careful that all of this happens in the right spot. So 5,000 times E, you'll find E in your calculator above ln usually, raised to the power of 0.035 times 5. I'm going to end that parenthesis and see what I get. Usually problems will tell you what to round to, but when you're dealing with money, we typically go to 2 decimal spots. So now to talk about the graphs with E. Hopefully you've done some exponential graphs before, and you know that they typically have an asymptote at y equals 0. And then if they're a growth, they'll start here and go up. If it's a decay, it'll be heading towards the 0. So this is no different. It's just instead of having something like 2 to the x, we have e to the x. So if I pick a few x's and plug them in, if I plug in -1, I would get 1 over e, which is going to be a decimal. So you can put it in the calculator. Most people round that to about 0.4. Putting in 0 always gives you 1. E to the 0 power is 1. And putting in 1, you get e, but we now know that's about 2.7. So if we plotted these at -1, I'm at 0.4. At 0, I'm at 1. And at 1, I'm at 2.7. So that's about here. So this is a growth. It is always going to be a growth if your base number is larger than 1, which E is. So now let's see what happens when we start manipulating and changing a few things, maybe flipping, maybe stretching, stuff like that. So in this case, our parent graph would be e to the x. So we could do the same thing we just did to kind of get our starting values. But now anything that happens in this exponent with the x is going to affect the x's, but we always do the opposite. So if there was a +2, I would subtract 2. But since there's a 1/2 being multiplied, I flip it. So I'm going to multiply all my x's by 2. Anything out front or in the back affects the y, and we don't do the opposite. So this negative out front is going to affect my y values. So going back to my parent graph, if I were to multiply all my x's by 2 and multiply all my y's by -1, these are the points I would have. Since we didn't move up or down My asymptote is still going to be at y equals 0 because the only thing that would affect that is moving the whole graph up or down. But if I plot -2, -0.4, 0, -1, and 2, sorry, -2.7, you'll see that the negative in the front flipped the graph. And the 1/2 made it stretch out a little horizontally. Okay, let's do some more with the word problems and money. So the equation we looked at before was for continuous growth, but sometimes it's only growing per day or per month or per year. So this is another equation to figure out your future value if it's not continuous. So again, this would tell you your future value of the money you put in. This is your initial. So the money you started with. R is still your rate, T is still your time, but this new letter N is going to be how many times it's getting compounded per year. So let's look at an example. Find the future value of the investment when it's compounded annually, monthly, daily, and continuously. So for the first one, annually, that means N is going to be 1. So our future value is going to be the 2,500 times 1 plus, we got to change our rate to a decimal, divided by 1, because that's what our N is, raised to the power of 1 times 6, because we're looking at 6 years. So you need to put this in the calculator carefully, but you should get this for your answer. So the only difference for B is they want us to do monthly. So instead, my N is going to be 12. So don't forget to put the 12 here and here. And this time we get a little bit bigger answer, which makes sense because it's compounding every month instead of just once a year. For C, we want to do daily. So daily means 365. So I think you could put 365 in for N. I'll just give you the answer so you could try it and check if you want. And finally, continuously means we're going back to P times E to the RT. So 2,500 times E raised to the R times the T. And that would get us this. So not a very big difference, but we got a little bigger each time. And then finally, it's saying find the doubling time. So we have not talked about this yet. The doubling time T for the given interest rate. Well, first of all, what it's basically asking is how long would it take your money to double? So if we're starting with 2,500, then they're basically saying how long would it take for that 2,500 to reach 5,000? So they're giving us the future value. There is a shortcut to this, though. So E raised to the R, but this time we don't know the T. Okay, so the shortcut is, because we want it to double, our first step is always going to be dividing by the 2,500 and getting a 2 here. So from now on, if you understand that, you can just start here whenever you're trying to find the doubling time. You can just ignore the actual amounts and just say 2 needs to equal E to the RT. So now how do we solve this? Here's where you need to remember something about solving with E and the fact that ln and E kind of wipe each other out. So the step to solve this will always be taking the natural log of each side. That's what ln is, so that you can get rid of the E, and now all you have to do is divide. So it's a nice trick that hopefully you've seen before. So this should be just a reminder that's how you would do it to get rid of that e and solve for t. Okay, here's a question that comes up a lot in calculus, not exactly these exact numbers, but something like this, where they give you a certain piece of information. In this case, they're telling us what ln4 is, and they're telling us what ln5 is. We could find that in our calculator, but this is a type of question where they're always going to want you to do it without your calculator. And the reason why is they're trying to see if you remember some of the basic rules of logs. So it's kind of like a puzzle. They're basically saying, could you rewrite this somehow to involve just ln4 or ln5 so that you could do it without a calculator? And the answer to this is yes, if you remember that 2 logs being added is the same as putting them together as 1 log being multiplied, which means since 20 is the same thing as 4 times 5, hopefully everyone agrees I could rewrite it this way if I want to. But now if you remember about logs, you would know that you could split that up. So now, since I can split it into ln4 plus ln5, and I already have those values, thanks to what they gave me, I can just add them together and see what I get. So again, this is just a type of question calculus teachers love to see if you remember some of the rules of logs. So in this case, what you need to remember is ln of 5 over 4, since that's like a division problem, is the same as me splitting it up into ln5 minus ln4. So again, now we could just subtract the 2 values they already gave us to get our answer. So next one, similar. I can split it up by subtracting. But this time you might say that we can't do any more because we don't have ln1, but that's another property you should know. You do know ln1 because the only way to get a 1 here in any log is if it equals 0. Because what you're really thinking is e to what power would get you to 1. So ln1 really equals 0. So I'm doing 0 minus ln4, which we know is this. So my final answer is just negative 1.3863. So the key to that one was remembering you could split it into subtraction, but also remembering that ln1 equals 0. And finally, this one is the same as e to the 8th raised to the 1/2, because that's what square roots are the same as 1/2 powers. So with rules of exponents, I could rewrite that as ln e to the 4th, because we can multiply the 8 and the 1/2. And now, since ln and e basically wipe each other out, the final answer for this one would be 4. So I don't even need any of these properties up here. Okay, how to solve with e, we already saw this once. So just a reminder that you can take ln of both sides, and that wipes out. If they tell you to round, then you would pick up the calculator and plug in ln10 and round to 3 decimal places in this case. For the next one, first you need to get rid of that 5, because the trick with the ln only works when you've gotten rid of anything extra. So now we can take ln of both sides, which gives us 2t equals ln3. So one more step, divide by 2. And that is our answer. If they want it as a decimal, we can put it in the calculator carefully. And finally, solving with ln. Same idea as far as getting the ln by itself, just like how we wanted to get the e by itself before we do anything fancy. So in this case, I'm going to subtract 1 and also get rid of that 4 out front by dividing. But now we are stuck. I'm just going to make 6 over 4 3/2. We are stuck. When you're stuck with an ln, you have to remember that you can always switch it to the exponential form. The exponential form, since there's really an imaginary e here, would be e raised to the 3/2 equals 2x plus 1. And now we can keep going. Subtract 1 and divide by 2. And again, you can put all of that into the calculator. If they're asking for decimals, just be careful. I'm going to raise e to the 3/2, but I'm going to end the parenthesis, then subtract 1. I'm going to go ahead and hit enter and then divide by 2, just to make sure it does everything in the right order. Okay, and one more of those. We have a lot of ln's here. If we only had one on each side, we could just ignore them. So the problem is that we have 2 on the left. So again, remember that you can change 2 logs into 1 log by squishing them together, which turns the addition into multiplication. So instead of having 2 logs, I just have 1 log if I multiply that stuff. Now that I have 1 log on each side, I can wipe them out and say this all equals 24. I'm going to go ahead and distribute. Now I have to factor, so I need to get everything on one side. So I'm going to subtract that 24 and then factor. So in this case, I could factor that to x plus 6 and x minus 4, which means my answers are -6 and 4. But with logs, you have to be careful. You need to make sure that if you plug those in, you would never be taking the log of a negative number or 0. It has to be positive. So -6 plus 2 is -4. So that will not work. 4 plus 2 is fine. A 4 here is fine. So my only answer to this will be 4. Okay, I know this is a lot, but there's a lot to review to make sure you're ready for the calculus stuff. So last thing is log graphs, specifically the ln graph, so the natural log. Because we have already done e to the x, it is easier to start with that. So remember, we just did this a minute ago. When we plugged in a -1, we said it was about 0.4. When we plugged in 1, it was 0. When we plugged in 0, it was 1. And when we plugged in 1, it was e, which is about 2.7. So logs are just the inverse of exponential graphs. So to do the ln part, all we really need to do is take this chart and switch x's and y's. So all of my x's become my y's, and all of my y's become my x's. And so instead of having y equals 0 as an asymptote, we're going to have x equals 0. Because again, x's and y's switch. So at 0.4, we're at -1. At 1, we're at 0. And at 2.7, we're at 1. So the graph ends up looking like that. So that is what the lnx graph looks like. So now, how do we manipulate that and change it around? Well, again, you can start with the graph e to the x. Then you can switch all the x's and y's to get it into ln form. So this is technically ln x. But now, what do we need to do here to make changes? Anything in here is going to affect the x, but again, opposite. Anything out here, or if there was something out back being added or subtracted, is going to affect the y's, and we don't do the opposite. So take all of my old x's and add 3. And take all of my old y's and multiply by 2. My asymptote is going to move this time because now that it's x equals 0, anything to the left and right will move it. So we have moved to the right 3. So that is where my asymptote is now. So 3.4, negative 2, 4, 0, 5.7, 2. We are now doing something like that. So there's just a quick reminder, hopefully, of graphing exponential graphs with E, graphing L and X, and also doing some of the word problems with the interest rates. Hopefully that helps. If not, I should have other videos on some of this. If you need more detailed information, you can let me know and I can send you the correct video. Hopefully that helps. Bye.